In this video, we're going to take a look at an example of how to design a PD compensator. So this example is going to go into a bit more detail, therefore our video is going to be a bit longer than normal. So we want to design an ideal derivative compensator to yield a 16% overshoot and have a 3-time reduction in our settling time t sub s compared to the original system, which is shown below. So we note in this original system we have unity feedback. It is negative feedback, so that's good. That's what we know how to deal with. And we have this G of S block, which has 3 poles and some gain k. So we know that our root locus is going to have the same general shape as what we considered in the previous video. So because we're trying to alter the original system and reduce the settling time, the first thing that we need to evaluate is what is the original system doing? So the first thing we want to do is evaluate original system performance. And so this is going to be sort of what we've looked at in previous units. So sort of tying all of this stuff together. So evaluate original system performance. And so the first thing that we want to do is ultimately we're looking for our dominant poles. And so we know that our system is operating at a 16% overshoot. So we want to find what our damping ratio is that corresponds to that. So we can go back to our previous equation that we looked at when we were dealing with time response. So our damping ratio is negative natural log of our percent overshoot. In this case, it would be 16 divided by 100. And that is divided by the square root of pi squared plus natural log squared, and then we have that same ratio of percent overshoot divided by 100. And so if we plug in our 16% overshoot, we find that our damping ratio in this case is approximately 0.504. Okay, so now what we can do, knowing this damping ratio, is we can go to MATLAB or some similar program. If we're in MATLAB, we can do our R locus function to plot our root locus. So R locus of G, we can do our S grid, and we can say S grid of 0.5040, and that's going to give us our zeta equals 0.504 line. And then we can use our rloc find function, and we can have that output to some gain and some pole parameters. So we can say Kp is equal to rloc find, and that is going to give us our dominant poles of interest if we find the intersection of the root locus and that damping ratio line. And so if you do that as an exercise in MATLAB, you should get values for the dominant poles at about, excuse me, about negative 1.205 plus or minus J 2.064. And again, that's approximate depending on exactly where you click. You might get a slightly different value. And so again, these are our dominant second order poles. And so if we're going to be using any of our equations for second order systems, we want to make sure that we can accurately approximate it as a second order system. So let's say we want to check our second order assumption. And so what that means is we want to look at the location of that third closed loop pole. So we know because we have this third pole in our original system, we're also going to have a third pole in our closed loop transfer function. So we want to see where that is, and if we have created a variable here to output, we should easily be able to check this pole variable. And so 2 of the entries are going to be these, and then our third entry, it turns out that it's going to be at, so let's see, our third pole is going to be at approximately negative 7.59. And so remember, when we're determining if our second order approximation is good enough, sort of our general rule is that we say if it's more than 5 times further left, then we can use our second order equations. So more than 5 times further left, and in this case we're comparing the negative 7.59 to our real part of our dominant poles. So we can say in this case that almost negative 7.6 is in fact more than 5 times further left than negative 1.2. So our second order approximation is going to be good. So with that in mind, we can now use our second order equations. So we had our settling time is equal to 4 divided by zeta omega n, excuse me, And so we know that our zeta omega n is really just the magnitude of the real part of our dominant poles. So that's going to be this value here circled above. So plugging that in, we know that this is 4. And again, it's just the magnitude, so 1.205. So negative settling time doesn't physically make sense. And so we get that that is approximately 3.320 seconds. Okay, so now we go back to our problem statement, and we're wanting to maintain this 16% overshoot, but we want a 3-time reduction in our TS. So a 3-time reduction in TS, of course, means that our new TS, so let's say our compensated TS, is just going to be equal to that value above divided by 3, which ends up being 1.107 seconds, approximately. And so now we need to figure out how, well, the first thing we're going to do is we're going to say, where do we need our pole to be in our updated root locus? And then we're going to figure out how we can add a 0 to move it to that position. And so we're going to draw these root locuses here in a little bit, but first let's figure out exactly where this new pole is going to be. So let's not paste that. So we know, again, that TS is equal to 4 over our sigma omega n, but now we're talking about for a compensated system. So to simplify things, we can say this is 4 over sigma d, so that was our real part. And we can solve then, plugging in this value of t sub s, and we can solve for our sigma d. So 4 over t sub s is going to be approximately 3.613. Now the reason we want to do that is we can look at our S-plane. So if we look at our S-plane here, I've got our damping ratio line for 0.504. And so what that's telling us is that this 3.613 is the magnitude of our real part. So we come over here and we know that we have at some point here negative 3.613 is going to be the location of our pole. So let me do that in a different color maybe. So let's do our closed loop pole in orange. But now what we want to figure out is what is this value on our imaginary axis here. So what, this is J something. So we want to figure out what that value is. And so we can do that by creating a right triangle. So if we create a right triangle here, so that's kind of rough, but a right triangle here, so we know the magnitude of that bottom side is 3.613. So that's the settling time, from the settling time we found there. Now we want to figure out basically what is this height over here. And so in order to do that, we need to know this angle down here. And so we can find that based on the relationship between our zeta and that angle. So remember, cosine of theta is equal to our damping ratio zeta. So if we do inverse cosine of 0.504, we see that this angle here is 59.7 degrees, approximately. So then we can use trig and we can say that this value here, this question mark value that's multiplied by our j, is just going to be 3.613 times the tangent of 59.74 degrees, and that gives us approximately 6.193. So we're saying that this value here is no longer unknown, it's 6.193. Okay, so what that tells us is this is our desired pole location. So our desired pole location is at negative 3.613, so that's our real part, which is giving us our desired settling time. And to keep that same damping ratio and therefore the same percent overshoot, we found that we need an imaginary part of J 6.193. So these are the desired pole locations then, and pole locations, because of course we're going to have a complex conjugate pair. So what we want to do then is we want to move our root locus from this initial dominant pole pair, which we see right here, to that new desired pole pair. And so as we talked about in the previous video, we're able to do that by adding a 0. So let's just say to move our root locus to desired point, we need to add a 0. However, in the previous video, we sort of glossed over where do we place that video. So it turns out that we have to have our 0 in a location such that our basic criteria for the root locus is still satisfied. And particularly what we're going to focus on is that the sum of our 0 angles excuse me, minus the sum of our pole angles has to be equal to some odd multiple of 180. So 2m plus 1 times 180 degrees, where m is just an integer value. So 0, 1, 2, so on and so forth. So basically, if we're looking at our S-plane, the angle has to be sort of in the negative direction on the real axis. And again, going back to our root locus unit, this was one of the two criteria that we had for a point to be on the root locus. So we need this to be satisfied. What we want to do then is let's start by looking at the angle of our existing poles, and from there we can figure out what we need to do, what 0 angle we need to add. Okay, so let's start by considering, excuse me, having a rough time today. So considering angles of our existing poles. Okay, so let's go ahead and get another root locus plot up here. So we're going to use the same sort of baseline. And I'm going to try my best to draw this accurately, but no guarantees, of course. So we've got -1, -2, -3, -4, -5, -6, -7. Okay, and so basically I'm just giving myself enough space here. So let me see, we had a pole at -6, -4, and 0. So we have a pole here, 0, 1, 2, 3, 4, and -6. So let me just go ahead and label those below as well. So that's -6, -4, and then of course 0. And using our basic root locus, what we can say is that our root locus is going to be on the real axis between 0 and -4. Let me make that a little bit larger. So between 0 and -4, we're on the real axis, and then to the left of -6, we're on the real axis. And so our direction is the -6 is just going to be going that way. We're going to have 3 asymptotes, similar to what we saw in the previous video, because again, our open loop transfer function has the same basic form. And what we're going to see is that it turns out somewhere around here, we're going to have a breakaway point, and our root locus is going to do something that looks like this. Okay, so remember though, this is our initial pole location. So let me mark this. So this is our initial pole location. And so going back to the value we had up here from our program, we said that was -1.2 plus or minus J2. So let's see if I can get this scale relatively accurate here. So coming over here, we can label this as, this is J1, J2, so we want to be just a little above J2. So there's J3, 4, 5, 6. So this is J6, this is J2. This is -1, -2. Okay, so that's our original pole location. So now our desired pole location we're looking for is at -3.6, and so this is where I kind of have messed this up a little bit, but we can kind of fudge our scale a little bit. So this is our desired pole location up here. So around -3.6, and that's a little above our, so this is -3.613 plus J 6.193. So again, not quite perfect, but it should be a little above this J6 point and a little past halfway here. So what we want to do is figure out our angles contributing to that desired pole location. And so how we're going to do that is we can draw lines from each of our open loop poles to that desired closed loop pole, and then we're going to talk about the angle between that and the real axis. So this would be theta P3. This one is going to be theta P1. Let's see if I can get that cleaned up a little bit. So this is going to be theta P2, and then we also have some angle here, which is going to go along this damping ratio line, and the angle between that and the real axis is going to be theta P1. So now our goal is to figure out what are those angles theta P1, theta P2, theta P3, and then we can come and we can plug that into this equation here and figure out what 0 angle we need in order to make the overall sum an odd multiple of 180. Okay, so in the notes, the method I have is a little bit awkward, and that's just because that the book was not very clear, and so I kind of had to go figure out stuff for myself, but I kind of fudged up the trig a little bit, and I made it a lot more difficult than it needed to be using the law of cosines, when in reality we can just use right triangles. So what I'm going to show here is the right triangles, but if you're looking in the notes, just know that that's a little more complicated than it needs to be. So the basic idea is that I'm going to make a right triangle here. So I'm going to make one here like this to find my theta P1. So let me go ahead and, well, let's look at all three of them. I can make another right triangle coming down here like this to find my theta P2, and then a third right triangle like this to find my theta P3. So I'm going to go ahead and draw these separate triangles out on a separate page, and you can refer back to this figure either here or in the notes if that's helpful. Okay, so let's draw that first triangle. So we had something that looks like this. See if that'll help me. There we go. That's a nice clean right triangle. So we know that this distance here is 3.613. This is 6.193. And we know that this angle here is theta P1. So this is theta P1, which is what we're interested in. And so using trig, we can say that our theta P1 angle is going to be 180 degrees minus, so we're subtracting it from this angle here, or we're subtracting this theta from 180 to get our theta P1. And so that angle theta is the inverse tangent of the opposite over adjacent, so that's going to be 6.193 divided by 3.613. And we plug that in, and you should get approximately 120.26 degrees. So similar approach for our other two angles. So let's draw another right triangle, and that's going to be like this for our theta P2, except now our theta P2 angle is going to be inside of the triangle, so we're not going to need that minus 180. And so we still have this height of 6.193. However, now our length of the bottom is going to be 4 minus 3.613. So this is going to be theta P2, which is equal to the inverse tangent of our 6.193 divided by 4 minus 3.613. And so if we plug that in, we get that this is approximately 86.42 degrees. So one more to go, our theta P3, and so that's going to be a similar right triangle sort of pointing towards the left there. And so now this angle inside is our theta P3. Our height is still going to be the same 6.193 that it is for all of our right triangles. And now our width on the bottom is going to be 6 minus 3.613. So similar equation as above, we have theta P3 is equal to inverse tangent of the opposite over adjacent, so 6.193 divided by 6 minus 3.613. Plugging that in, we get that theta P3 is approximately 68.92 degrees. Okay, so now we have our three pole angles. So 120.26, 86.42, and 68.92. So we want to sum all of those up, so we can say the sum of our pole angles, if you add all of those up, ends up being approximately 275.6 degrees. So remember, for our desired point on the root locus, or for our desired point to be on the root locus, we need to have the sum of our zero angles, which we're going to add one zero. So let's say theta sub zc plus the sum of our pole angles. And so let me see if I've written that, if I've made a mistake on the previous one. We should have had minus the sum of our pole angles. Okay, we do, so I would just set it wrong there. So we're subtracting the sum of our pole angles. So we're subtracting this 275.6, and we want that to be an odd multiple of our, we want it to be an odd multiple of 180. And so the closest odd multiple of 180 is going to be negative 180, just based on the fact that this is negative 275 and this is going to be some positive angle. The closest one, or the smallest theta cc, is going to be positive, and plugging that in, we get that this is equal to, or sorry, we don't get that, that's equal to, we get that our theta zc is approximately equal to 95.6 degrees. Okay, so now we know our desired 0 angle. So if we come back up to this diagram here, we know that we have an angle of 95.6, so it's not quite going to be right below this point, but rather it's going to be a little bit to this side because that's a little bit greater than 90. So what we're going to do is a right triangle that looks something like this, okay? And so what that right triangle is going to be then, so let's come down here and draw that. So we're going to have something that looks like this. See if I can get it to go the right way. So it's going to be a relatively narrow triangle is why I'm trying to draw it sort of small like that. So we still have the same height, 6.193. We have in the bottom here, this is going to be 3.613 minus alpha. And so alpha is going to be the location of our 0. And so basically we said we know that our 0 is going to be a little bit sort of to the right of that 3.613. And so that location we're calling alpha. And so we're saying the distance then here is our 3.613 minus the alpha. Okay, so that's what we're trying to solve for, is that alpha, which is going to be our 0 location. And we know this angle here is going to be our theta sub theta sub CZ, which is 95.6 degrees. So again, we go back to using our trig, and if we solve that, we find that our sigma is going to be equal to 3.613 minus 6.193 divided by tangent of 180 minus 95.6. So just subtracting 95.6 to get this angle inside here, and then using our basic tangent relationship. If we plug all of that in, we get that our sigma is approximately 3.006. And so what that tells us then is that we want to insert a 0 at the point negative 3.006. So coming back up here, we can see that's more or less what we had drawn with this line here, so just a little bit past -3. So we would insert a 0 there. So let's take a look at what our updated root locus is going to look like. Okay, so let's come down here to this next page and let's go ahead and put that sort of base root locus here. And so now we have, let's see, we have -1, 2, 3, 4, 5. Let me do that a little better so it's more consistent with our other one. 3, 4, nope. Yeah, okay. Sorry, trying to get the scale roughly right. 4, 5, 6. Okay, so that looks pretty good. And so now we've said we still have our we still have our pole at 0. We still have a pole at -4, so 1, 2, 3, 4, and a pole at -6. And now we've introduced this 0 just right above -3. So right about here we have our 0. And so our desired pole location is at about -3.6. So let's put that about here. And that's going to correspond to, being a little above -J6 over here. So we'll go ahead and put that there for clarity. So that's about J6 right there. Okay, so let's sketch what our root locus looks like. So let's switch over to blue, and we know on our real axis, it's going to be on the axis between 0 and our, have I forgotten a 0? No. So it's going to be between here, between our pole at 0 and our 0 that we inserted at -3, and it's going to be on our real axis between here. Now, we have 3 finite poles and 1 finite 0, so we're still going to have 2 asymptotes. We're going to have a breakaway point somewhere between those left 2 poles at -6 and -4, and we're going to have this pole just going towards that open loop 0 a little past -3. So these 2 are going towards each other like this, and at some point they're going to break away, and we're going to see something that looks like that. And so again, I'm not necessarily doing a great job of drawing that accurately in terms of scale. You could find the theta sub A and the sigma sub A for the asymptote and draw that a little more accurately. Now, of course, this is our desired pole location that we designed for, so -3.613 plus J6.193. So of course what we want to do though is we want to check the location of our third pole. So what we're calling our dominant poles are going to be here, and of course there's going to be a complex conjugate somewhere down here. But we want to know the location of this third pole, which is going to be in this region here. And so it turns out if we use that rlocfind function or a similar program, we can find that that third pole location is at about -2.8. So we're somewhere around here when we have the same gain to give us our desired closed loop pole up here. So let's write that out as well. So we have our third pole, and this is our third closed loop pole, I should specify. Is going to be at -2.775. Now, ideally, what we would like to have is we would like to have this pole and this 0 canceling out, but they're just not quite close enough. So it's pretty close, but for most approximations, that's not going to be quite accurate enough. So let's say not quite close enough for pole 0 cancellation. And therefore also not quite close enough for a second order approximation. So what that means then is we wouldn't necessarily want to do those second order equations to be very accurate. If we wanted to have more accurate results, we would want to turn to doing simulation. And so that means we could use our step function in MATLAB with our closed loop transfer function t, and we could figure out our exact settling time, percent overshoot, damping ratio, all of that stuff. And so there are more detailed results provided on page 376 in the 8th edition textbook. And so those are contained in table 9.3. And so that just shows a lot of interesting stuff that I've not covered here. So for instance, it shows the relationship between our uncompensated system and our compensated system. And so it's talking about our pole locations, which we've covered here, but it's also talking about the gain for each of those points. It's talking about the percent overshoot. And so what we can see is because in our compensated system, we can't quite use a second order approximation, we see that if we simulate it, we actually get a percent overshoot that is closer to 12% as opposed to the designed 16%. So there are a couple other things of interest in there as well. So they have, of course, the third pole, the 0, all of that stuff. But they also have some information about the steady state error. So I definitely recommend you take a look there and make sure you understand all of those pieces of information as we're really sort of starting to bring all of the stuff we've learned through the semester into one problem.